Good morning, all. I am Sailaja, working as assistant professor in the Department of Physics of Mlritm. Today, I am going to discuss about photoelectric effect. Before going to discuss what is photoelectric effect, let us first revise what we have studied in the last class. The last class we have discussed about introduction to quantum physics and blackbody radiation. Under introduction to quantum physics, we have studied what is classical mechanics, its failures, how quantum mechanics has evolved and its assumptions. Next, under blackbody radiation, we have studied what is thermal radiation, what is blackbody radiation, construction of Ferri's blackbody, and we have seen the spectrum of blackbody radiation. What is classical mechanics? Classical mechanics is a branch of physics which deals with the motion of macroscopic objects. It is introduced by Newton. According to classical mechanics, we know that oscillating electrons radiate energy continuously. Now, in order to explain experimental curves of blackbody radiation, Max Planck in 1900 introduced quantum theory. Max Planck derived an expression for energy distribution of blackbody called as Planck's law. It is given by E lambda d lambda is equal to 8 pi hc by lambda power 5 into 1 by e to the power of hc by lambda kt minus 1 d lambda. This formula agrees well with experimental curves throughout the whole range of wavelengths. So, this and according to that means quantum mechanics is a branch of physics which deals with the motion of microscopic objects, and according to quantum mechanics the energy of the electron is discrete. Now, under blackbody radiation we have studied thermal radiations. What is thermal radiation? The energy emitted by a body by virtue of its temperature is known as thermal radiation. Thermal radiation is an inherent property of all bodies. We have also seen that according to Prevost theory of heat exchange, every body emits or absorbs radiation continuously as long as its temperature is above 0 Kelvin. That means when the temperature of the body is greater than its surroundings, then emission is greater than absorption. When the temperature of the body is less than its surroundings, then absorption is greater than emission. If the body and the surrounding is at same temperatures, then also absorption and emission takes place. But in this case, absorption and emission takes place in equal amounts. Next, we have defined what is blackbody. Blackbody is a body which absorbs radiation of all wavelengths incident on it. It neither reflects nor transmits any of the incident radiation. Therefore, it appears black in color, whatever may be the color of the incident radiation. Next, we have defined what is blackbody radiation. The radiation emitted by a body when it is heated is known as blackbody radiation. Next, we have seen the construction of Ferri's blackbody, and next Lummer and Prinkstream, they have performed an experiment and they have plotted a graph between intensity or energy and wavelength for different temperatures. From these graphs, we have observed that the first point is energy is not uniformly distributed. Second point, we have seen that at a particular temperature, as wavelength is increasing, energy increases, becomes maximum and then decreases. And the third point is the wavelength corresponding to maximum energy is represented by lambda m, and we have seen that as temperature is increasing, lambda m shifts towards shorter wavelength. So, these all are the points which have discussed in the last class. Now, let us define what is photoelectric effect. Photoelectric effect: when light or any other radiation of suitable frequency or wavelength is incident on the surface of the metal, emission of electrons takes place from the surface of the metal. This phenomena is known as photoelectric effect. This effect was first observed by Hertz in 1887. This effect was observed by Hertz in 1887 when he allowed ultraviolet light to fall on zinc plate, and this afterwards it is also observed that when ordinary light falls on alkali metals such as sodium, potassium, lithium, etc., also this effect was observed. That means this effect was first observed by Hertz in the year 1887 when he allowed ultraviolet light to fall on zinc plate. Afterwards, it was also observed that when ordinary light falls on alkali metals also, emission of electrons takes place from the surface of the metal. Now, the electrons emitted in this phenomena are known as photoelectrons, and the current produced due to these photoelectrons are called as what? Photoelectric current. Now, photoelectric effect is an evidence for the particle nature of light. Now, let us try to understand this definition in detail. So, this phenomena is saying that when light of suitable frequency is incident on the surface of the metal, emission of electrons takes place from the surface of the metal. When light of suitable frequency, here so the suitable frequency is very important. Why? Because we know that light consists of different colors of different frequencies. Light is consisting of different colors having different frequencies. So, all these frequencies are not responsible for the emission of electrons from the metal. Why? Because different color frequency will have different frequency. Different colored light will have different frequencies. So, all frequencies are not responsible for the emission of electrons. For example, here a particular, that means only a particular frequency of light or light of suitable frequency is responsible for the emission of electrons from the surface of the metal. So, this particular frequency of light we are calling it as what? Threshold frequency. Okay, so when light of suitable frequency is incident on the surface of the metal, emission of electrons are taking place from the surface of the metal. Here this term suitable frequency is very important. Why? Because we know that light consists of different frequencies, different colors having different frequencies. So, all these colors are not responsible for the emission of electrons from the surface of the metal. For example, when light consists of different colors, VIBGR. So, all these have different frequencies. So, all these frequencies are not responsible for the emission of electrons from the metal surface. So, only a particular frequency will give the emission of electrons. On that particular frequency of light we are calling it as threshold frequency. So, now let us define what is threshold frequency. Threshold frequency means it is the minimum frequency of incident radiation which causes photoelectric effect. At this frequency only electrons are emitted, but it does not give any additional energy to the electrons. Threshold frequency means this frequency will only emit electrons without providing any additional energy to the electrons. That means its kinetic energy will be 0. At threshold frequency, kinetic energy will be 0. So, threshold frequency means it is the minimum frequency which causes photoelectric effect. If the frequency of incident radiation is less than threshold frequency is represented by mu naught. If the frequency of incident light is less than threshold frequency, no photoelectric effect occurs. If frequency of incident light is greater than threshold frequency, then photoelectric effect occurs. Here photoelectric threshold frequency is also a function of photometal used. It is a function of photometal used. Photoelectric effect is a not photoelectric effect, threshold frequency. Threshold frequency is a function of photometal used. That means threshold frequency is not same for all metals. It will be different for different metals. So, here we have defined threshold frequency. So, here suitable frequency point is very important. Why? Because we have said that light consists of different colors having different frequencies. So, all these frequencies are not responsible for emission of electrons. Only a particular frequency will emit electrons from the surface of the metal. That particular frequency we are calling it as what? Threshold frequency. Threshold frequency is defined as the minimum frequency of incident radiation which causes photoelectric effect. And at threshold frequency, this frequency will only emit electrons without giving them additional energy. That means kinetic energy is 0. If the incident frequency is less than threshold frequency, no photoelectric effect occurs. If the incident frequency is greater than the threshold frequency, then photoelectric effect takes place. And one more important point here is threshold frequency is a function of photometal used. That means the electrons is not emitted for all frequencies. Threshold frequency is a function of photometal used. That means threshold frequency is not the same for all metals. It will be different for different metals. So, let us try to understand threshold frequency with an example. So now here let us consider a metal surface here. This is a metal surface. Okay, and now allow light to fall on this metal surface. We have taken a metal, we are allowing light to fall on this metal surface. We know that light consists of photons. Light consists of what? Photons, and energy of the photon is given by E is equal to h nu. Energy of the photon is given by E is equal to h nu. Since h is constant here, we can say E is proportional to frequency, or E is depending upon frequency. That means if frequency of incident radiation is more, then energy of the photons will be more. If frequency of incident radiation is less, then energy of the photons will be less. That means whenever light is falling on the metal, then what is happening? One photon is completely absorbed by one electron. One photon is absorbed by one electron, and by absorbing the photon energy, electron is emitted from the metal surface. Here energy of the electron, energy of the photon is depending upon frequency. So whenever photon is falling on the metal, one photon is completely absorbed by one electron, and electrons are coming out of the metal here. So here in the case of metal, we take for example the metal surface as potassium. Just now we have said that threshold frequency is a function of photon metal. That means threshold frequency is not same for all metals. For example, you take sodium. For sodium, the energy required by the electrons to come out of the metal is 2.75 electron volts. Similarly, if you take potassium, for potassium, the energy required by the electrons to come out of the metal surface is 2 electron volts. And for lithium, it is 2.5 electron volts. Okay, so here we know that threshold frequency is a function of photometal. That means different metal requires different energy for the electrons to come out of the metal. For example, here we take the metal surface as potassium. So taking the potassium, now you allow different monochromatic light to fall on the surface of the metal. Monochromatic light means single colored light or single frequency light. That means here we have taken the metal surface has potassium, and now you vary the frequency. Varying the frequency means you are allowing different colored light to fall on the metal surface. So first you allow red light to fall on the surface of the metal potassium. So now we know that potassium requires 2 electron volts for the electrons to come out of the metal. Potassium requires 2 electron volts to come out of the metal, for the electrons to come out of the metal. So frequency, what is the frequency? From this table you can see frequency of red light is how much? 400. Here color of the light, first we have made red color to fall on the metal. So what is the frequency of red color light here? It is 400 Hertz. You know the frequency, you can calculate its photon energy. Its photon energy is how much? 1.65. This is the photon's energy. Photon energy is 1.65 electron volts. How you will get the photon energy? We know E is equal to h nu. H is Planck's constant. Nu is how much here? 400 Hertz. When you multiply these two, you will get the energy of the photon. E is equal to h nu. So first we allow red light to fall on the potassium metal surface. So its frequency is 400 Hertz, and what is the energy of red light here? Photon's energy is how much? 1.65 electron volts. But here the electrons here will require how much? 2 electron volts to come out of the metal surface. So since here the frequency of red light is less than the frequency that is required by the electrons here, so in this case what is happening? No electrons are emitted. No electrons are emitted here. Now you allow orange light to fall on the surface of the metal. What is the frequency of orange light here? 484 Hertz. 484 Hertz, and its photon energy is how much? 2 electron volts. 2 electron volts. So here potassium also requires 2 electron volts. So when orange light is falling on the potassium surface, what is happening here? Electrons are just emitted, but their kinetic energy will be 0. Electrons are only emitted from the metal surface, its kinetic energy will be 0. So here electrons are emitted but kinetic energy is 0. Now you allow blue color light to fall on the surface of the potassium metal. So you see the frequency of blue light is how much? It is 606 Hertz and its photon energy is 2.75 electron volts. So here potassium requires only 2 electron volts. So by using 2 electron volts, electrons are emitted from the surface of the metal and remaining 0.75 energy is used as kinetic energy. So in this case, what is happening here? Electrons are emitted as well as it is possessing some kinetic energy. It is also having some kinetic energy. Okay, so from this now we can define what is threshold frequency. So you can see this here orange light we are calling it as threshold frequency. The frequency of orange light is called as threshold frequency. Why? Because here we can see this frequency is only emitting electrons but its kinetic energy is 0. That means this frequency only emits electrons without giving them additional energy. So this type of frequency is called as what? Threshold frequency. It is denoted by nu naught. And we can see this, the frequency of red light is less than the frequency of threshold frequency, therefore no electrons are emitted. And here the frequency of blue light is greater than the frequency of threshold frequency, therefore here electrons are emitted as well as they are possessing kinetic energy. So from this we can say that whenever the incident frequency is less than threshold frequency, no electrons are emitted. When incident frequency is greater than threshold frequency, electrons are emitted. Okay, so this is an example of a threshold frequency. So next we will see the experimental study of photoelectric effect. So this figure shows the experimental setup of photoelectric effect. Here we have taken two metal plates P and C. These two metal plates are placed inside a evacuated quartz chamber. Now P acts as emitter. P is acting like emitter and C acts like a collector. So C is nothing but positively charged anode and P is negatively charged cathode. The plate P is connected to negative terminal of the battery and plate C is connected to positive terminal of the battery through galvanometer G. So this is a experimental setup. Now let us see what happens when voltage is 0. Voltage is 0 and no light is falling on the metal plate. When voltage is 0 and no light is falling on the metal plate, then galvanometer shows 0 deflection. Now voltage is 0, you allow light to fall on the metal plate. When light is falling on the metal plate, electrons are emitted and they reach towards a collector. Because of this, there will be current flow in the circuit and galvanometer shows some deflection. So this shows that when light falls on metal surface, electrons are emitted. So from this experiment, we say that whenever light falls on a metal surface, electrons are emitted. Now let us plot a graph between current and voltage, photoelectric current and voltage. So this is V on the x-axis and current on the y-axis. So first, when V is equal to 0, when voltage is 0 and light is falling on the metal plate, what is happening? Electrons are emitted and because of this there will be some current flow in the circuit and galvanometer is showing some value, current value. So at V is equal to 0, you have a current here. Now you increase the voltage. We call this as positive voltage. When you increase the positive voltage of plate C, what is happening? Photoelectric current increases and it becomes maximum. This maximum value of current is known as what? Saturation current. Maximum current is known as saturation current. For example, here at plate P, when light is falling on the plate P, 10 electrons are emitted. Okay, so these 10 electrons will reach the collector C as you increase the voltage. For example, at 2 volts, 3 electrons may reach the collector. At 5 volts, 8 electrons may reach the electron. Similarly, suppose at 8 volts, all electrons are reaching the collector C. So due to this, at 8 volts, all 10 electrons are reaching the collector. Due to that, the current may be some 9 amperes. So 9 amperes is your saturation current. At 8 volts, maximum current is 9 amperes. That means at saturation current, all the 10 electrons emitted by the plate P are reaching the plate C. Now, after reaching the saturation current, if you still increase the voltage, what is happening? Current is remaining constant. Why current remains constant here means all the 10 electrons which are emitted here, they have reached the plate C. Now, there are no electrons to reach the plate C. After 8 volts, if you still give the voltage, though you are giving voltage, there are no electrons left at plate P to reach C. So, therefore, there will not be any change in the current remains constant. So, now you apply negative voltage to plate C. As you increase positive voltage, what is happening? First, current increases and becomes maximum. Maximum current is known as saturation current. If you still increase the voltage after reaching maximum current remains constant. Now, you are applying negative voltage to plate C. When you apply negative voltage to plate C, what happens? Negative voltage means here you have to interchange the terminals of the battery. That means now you have to give negative, now negative terminal of the battery is connected to cathode and positive terminal is connected to plate P. Negative terminal is connected to plate C, positive terminal is connected to plate P. This positive terminal, this is negative terminal. Applying negative voltage to plate C is nothing but negative terminal of the battery is connected to plate C, whereas positive terminal is connected to plate P. Now you increase the negative voltage. When you apply negative voltage, what is happening? Now the negative charge is accumulated on plate C. Okay, so here negative charge is accumulated on plate C and electrons are also negatively charged. So what is happening when negative voltage is given to plate C, negative charge is accumulated on plate C, we know that electrons are also negatively charged. So due to this, repulsion takes place and electrons, they go back. They move in the backward direction. So due to this, what happens? As negative voltage is increasing, current slowly decreases and at one point, current becomes 0. So the voltage at which current is becoming 0, that voltage we are calling it as what? Stopping potential. It is represented by V0. So stopping potential is defined as the negative potential of plate C at which photoelectric current becomes 0 is called as stopping potential. It is represented by V0. It is also defined as the value of retarding potential difference between the two electrodes which is sufficient to halt most energetic photoelectrons. That means how much voltage we are applying to stop the most energetic electron is known as stopping potential. Stopping potential is defined as the negative potential of plate C at which photoelectric current becomes 0, or it is the voltage which we are applying in the opposite direction to stop the electron or to make the kinetic energy of electron 0. So here when positive potential is applied, to plate C, what is happening when positive potential is applied? When we apply positive potential to plate C, that means this positive potential will attract electrons towards it. Positive potential attracts electrons. It is attracting electrons means what? Its velocity is increasing. That means acceleration of electrons is increasing. That means applying positive potential to plate C implies that we are giving accelerating potential. Positive potential is also known as accelerating potential. Why? Because since it is increasing the velocity of electrons or accelerating electrons, we call positive potential as accelerating potential. When you give negative potential to plate C, what is happening? Since the plate is negatively charged and electrons are also negatively charged, they are getting repelled. That means electrons are moving in the backward direction. That means their velocity is decreasing. Decreasing velocity is also known as deacceleration. Deacceleration is also called as retardation. Therefore, negative potential is called as retarding potential. Positive potential is called as accelerating potential. Negative potential is called as retarding potential. Why? Because positive potential accelerates the electrons, whereas negative potential deaccelerates the electrons. Deacceleration means it decreases the velocity of the electrons. Therefore, we call it as retarding potential. So next we see the characteristics of photoelectrons. So from this graph we observe that when the positive potential of plate C is increased, photoelectric current also increases and reaches a maximum value known as saturation current. You can see here, as you increase the positive voltage is also known as what? Accelerating voltage. Negative voltage is known as retarding potential. As the positive voltage is increasing, current is increasing, it is becoming maximum, known as saturation current. If the potential of plate C is made negative, the photoelectric current decreases and finally becomes zero at a particular value. The negative potential of plate C at which photoelectric current becomes zero is called stopping potential. So this is your stopping potential. The stopping potential is independent of the intensity and saturation current is proportional to intensity. So from this graph what we can see here, we are varying the intensity. You can see I3 is greater than I2 is greater than I1. You are varying the intensity. How you are varying intensity means you have to change the power of the bulb. First you assume that the power of the bulb here is 100 watts, here it is 300 watts and here it is 500. So as you are increasing the intensity, what is happening to stopping potential? There is no change in the stopping potential. That means we can say that intensity is independent of stopping potential. For all the three intensities, stopping potential is having same value. So the stopping potential is independent of intensity. Now what is happening to saturation current? Saturation current means maximum current. This is the saturation current of I1. This is the saturation current of I2. This will be saturation current of I3. So as the intensity is increasing, what is happening to saturation current? Saturation current also increases. So saturation current is proportional to intensity. From this graph we can say that stopping potential is independent of intensity and saturation current is proportional to intensity. As intensity is increasing, saturation current is also increasing. Next, Einstein's photoelectric equation. Now according to Einstein, we know that the energy of the photon is used by the electron in two parts. Just now we have seen that whenever light is incident on the metal, one photon is completely absorbed by one electron and electrons are emitting from the surface of the metal. So that means here energy of photon is used by electron in two parts. First one, a part of energy is used to free the electron from the metal and that energy we are calling it as what? Work function. It is denoted by W naught. A part of energy is used to free the electron from atom. This energy is known as work function. The other part is used in giving maximum kinetic energy to the electron. It is denoted by half mv maximum square. So now that means here the photon energy is h nu. This is used by electron in two ways. First one, a part is used in freeing the electron from the atom, that we are calling it as W naught, and remaining energy is used as kinetic energy, that is half mv maximum square. So now we can write h nu is equal to W naught plus half mv square. So therefore h nu is equal to W naught plus half mv square. This is the photon's energy. It is used by electron in two parts. One is as work function, other one is kinetic energy. So this is known as Einstein's photoelectric equation. Now when the energy of photon can only liberate the electron from the metal, the maximum kinetic energy of the electron will be 0. So this is nothing but the definition of a threshold frequency. So that means what here, the frequency is only liberating electrons. It is not giving them any additional energy, means we call that frequency as what? Threshold frequency. So now in this equation 1, from this definition, what this is saying, that means kinetic energy is 0. So therefore in equation 1, in the place of kinetic energy you substitute 0, and when kinetic energy is 0, then the frequency of the electron is represented by what? Nu naught. So therefore equation 1 becomes what? H nu naught is equal to W naught. In equation 1, kinetic energy is 0. So half mv maximum square is 0, and when the electrons are only emitted and it is not possessing any kinetic energy, then at that time the frequency of the light is known as what? Threshold frequency. Therefore we are representing here this nu by nu naught. So this equation becomes what now? H nu naught is equal to W naught. So where nu naught is called what? Threshold frequency. So threshold frequency we have already defined it as what? Minimum frequency of incident radiation which can cause photoelectric emission. This effect occurs above this frequency while ceases below this frequency. Ceases means Below this frequency, this effect stops. This effect does not occur. Threshold frequency is a function of photometal. Now you substitute equation 2 in equation 1. Substituting equation 2 in equation 1, what you will get, h nu is equal to h nu naught plus half mv maximum square. From this equation, half mv maximum square is equal to h nu minus h nu naught. Here we are writing expression for half mv maximum square. So here half mv maximum square is equal to, what happens, this will go this side. So h nu minus h nu naught. If v naught is a stopping potential, then so we know the second, what is the second definition of stopping potential? Stopping potential is nothing but the potential which we are applying in the opposite direction to make the kinetic energy of the electron 0. That means here kinetic energy of the electrons will be equal to the potential difference between the two electrons. So what is the formula for potential difference? Potential difference is, this formula for potential difference is charge into voltage. So what is the charge of the electrons here? E, and voltage is stopping potential V naught. So here kinetic energy of the electrons will be equal to EV naught. So this equation 4, now you substitute in equation 3, then what we will get here in equation 3, in the place of half mv maximum square, we are substituting EV naught. So EV naught is equal to h nu minus h nu naught. So from this, what will be the equation of V naught here? Substituting equation 4 in equation 3, we got EV naught is equal to h nu minus h nu naught. Now V naught will be equal to h nu naught by h nu by E minus h nu naught by E. This is equation number 5. And this equation is similar to equation of a straight line having y-intercept. What is the equation of straight line having y-intercept? That is y is equal to mx plus c. So now compare equation 5 with this equation. You can see in the place of y, what we will get here? V naught is equal to h nu by E minus h nu naught by E. Compare these two equations. In the place of y, we have stopping potential V naught. In the place of x, you are having a new frequency. In the place of m, we have h by E. And in the place of c, we have minus h nu naught by E. So on y-axis, we are taking stopping potential. On x-axis, you are taking frequency. So now you plot a graph. See here on x-axis, you are having frequency. On y-axis, we are taking stopping potential. Now what is happening? You are getting a straight line that is having negative y-intercept. What is m here? Slope of the line. M represents slope, c represents the y-intercept. So slope is how much? Slope of this line is h by E. And what is a negative intercept here? Minus h nu naught by E is a negative intercept. So this equation is saying you that we are plotting a graph between frequency and stopping potential. You get a straight line having slope h by E and its y-intercept is minus h nu naught by E. And what are the, one more thing what we are observing here is, at nu naught, what is happening? At nu naught, stopping potential is 0. Nu naught means threshold frequency. See, this is your threshold frequency. At threshold frequency, stopping potential value is 0. That means we know that threshold frequency means it only emits electrons, kinetic energy is 0. So when you apply stopping potential is used to make the kinetic energy 0. Kinetic energy of electrons is 0. At threshold frequency, since there is no kinetic energy, stopping potential, no need to apply stopping potential. So stopping potential value is 0. So at threshold frequency, stopping potential is 0. Now this above threshold frequency, what is happening? This is above this frequency. Above threshold frequency, as frequency is increasing, kinetic energy increases, therefore stopping potential also increases. If frequency is decreasing, kinetic energy decreases, stopping potential also decreases. And below mu naught, below threshold frequency, but this in this part, stopping potential value is negative. Stopping potential cannot have negative values. Stopping potential maximum value is how much? 0. Stopping potential maximum value is 0. It cannot have negative values. So what this is indicating means, this we are showing it by dotted line here. This is an imaginary line, and this line indicates that whenever the frequency of incident light is less than threshold frequency, photoelectric effect does not occur. And when nu is greater than nu naught, threshold frequency, when nu is greater than nu naught, that means incident frequency is greater than threshold frequency, then photoelectric effect occurs. Okay, so this region indicates nu less than nu naught, and this region indicates nu greater than nu naught. So only in this region photoelectric effect takes place. In this region photoelectric effect does not takes place, and that is represented by a dotted line here. So this dotted line indicates that photoelectric effect does not occur when nu is less than nu naught, and whenever nu is greater than nu naught, photoelectric effect takes place. Next, applications of photoelectric effect. Two of the most important applications of photoelectric effect are photoelectric cell, photocells or solar cells. Photoelectric cells are used in television, in burglar alarms. In burglar alarms means whenever you go to some museum, if you touch anything, it will give a sound, it will give alarm. So that in such type of alarms, we are using this photoelectric cells. In counting machines, as micrometer, in automatic switching of street lights, in automatic door opening circuits. So these are the applications of photoelectric effect. These are the references. Okay. So thank you.